Hello, everyone. In this lecture, we're going to discuss the continuous time Markov chain case study, dealership market, car dealership market. So this is an outline. First, we're going to have a look at the problem together, the car dealership market. And then we're going to discuss how to use the CTMC to model this market dynamics. So specifically, we're going to talk about MM1KQ modeling. And then we're going to talk about the cost models and policy analysis. So this case study is primarily from this paper, Dealership Market Making with Inventory from Journal of Financial Economics. So first, let's have a look at the problem. We have a small car dealership, buy and sell used cars. The sale pricing is 10% markup over the purchase price. For example, for this model, you see here, we have 5 car models labeled 1, 2, 3, 4, 5. So if we purchase this model 1, car model 1, then with $8,000, the sale price will be 10% up, 8,800. We have supply. Supply is how many cars per week, and people come to sell their cars to the dealership. Those kind of supplies, all from other places, other supply chain. Then they got cars every 20 cars. They can get 20 cars per week. But they don't necessarily to take all 20 cars because their parking lot is limited. They can this dealership can only hold at most 40 cars. But they have to hold all the 5 models, or some of them. So now the question is, how many cars should be stocked for each model? And as we can see, the supply and demand changes for each car model. And the price is also different. But although the sale price is always 10% markup over the purchase price. Okay. Now the stocking policy. Stocking policy, we can have like K1, K2, K3, K4, K5 stock at most KI cars of model I. That means for model I, for model 1, we stock K1. And the constraint is K1, K2, K3, K4, K4, K5. Yeah, add them together has to be smaller than the capacity, 40 cars. The space we have in the parking lot. So now we have a policy 1. That means average. We give 8 to each car model. Okay, 8 spaces to each car model I. Thus, the dealer won't buy a car of model I if there are already 8 cars of that model in his lot. So policy 2 is 0.7. So we don't buy any, we don't stock any model 1 because it's too cheap. And then 7, 14, 7, 12. How did we get this policy? This is based on this logic. The number of spaces allocated to a model should equal the smaller of the weekly supply and demand. And the space should be prioritized to allocate to the most expensive, hence more profitable models first. So obviously this one is, model 5 is more expensive. So smallest of the demand and the supply, so it's 12. So we allocate this one 12 first. And then this one is the second most expensive one. So we allocate 7, so 7. Then 14, and then 7. So we only have 7 left, okay? Because total is 40. So 0 model 1. Now, people can come out with different policy because there are many combinations less than 40. Now we're going to analyze this too. The question is, which one is better? And also, is there any like optimal stocking policy that the dealership can use? So these are 2 questions we are trying to answer with the CTMC model. So CTMC model, So let's have a look at the car model 1. So sellers arrive according to a Poisson process, like lambda. The rate lambda equals to 20 per week. The buyers arrive, okay? Poisson process, rate mu. Mu is 16 per week. You see here, this is supply, 20, and demand is 16. Okay, so buyers arrive and the 16 per week. So capacity in the parking lot is K, suppose it's K. Now, XT is the number of cars, model 1 at time T. Obviously, the allocated stocking capacity is K, so the state space can go from 0 to K. So the sellers arrive and the buyers arrive, they come in a random fashion according to Poisson process. So the rigid diagram will be, for example, you have 0 and then somebody come to sell their car, so the supply, so you are going to increase to 1. But if a buyer comes, you're going to sell it, this rate, okay? So the inter-arrival time is, because it's Poisson process, so its inter-arrival time is IID exponential. And the service time or the sell time is also exponential. So this is a typical burst test process. Okay, and it's a M1KQ. So this M denotes the arrival process, and M means memory-less exponential inter-arrival time exponential. This M is a departure process or service time, and M also denotes exponential. And the memory-less. 1 is number of servers. It can only go 1 at a time. And so we have capacity K. Okay. Now, this is a finite burst and death process. So mu 0 equals to 0 because you don't know death in state 0. So it goes from previously, we see the lambda mu, they are all equal, mu is not equal. Now let's have a look at the general case. So we have lambda 0, lambda 1, lambda 2, lambda 3, lambda k minus 1, and then mu k. That means burst rate and death rate depending on the state where you are right now, okay? And in the previous slide, we actually make the lambda I all equal to lambda, the constant, they're all the same, and the mu I is all the same. So we're going to look at the complicated case with different values of lambda I and the mu I, depending on the state first. And no burst in state K, because this is a capacity. Lambda K equals to 0. So for the general burst test process, and we have the balance equation is lambda 0, P0, and equals to mu 1, P1. So lambda 0, okay, and mu 1. For 1 is actually lambda 1, see here, lambda 1 plus mu 1, this is to go outflow, and inflow is lambda 0, mu 2. So they got to achieve a balance. So lambda 1, mu 1 times P1 and equals to lambda 0, P0, enter, lambda mu 2, P2, enter the state 1. And similarly, we can achieve for every state, So now, based on this balance equation, we want to derive the limiting distribution. So here, the limiting distribution, limiting behavior. We want to know P1, P0, P1 to Pk, okay? So let's suppose we put rho 0 equals to 1, and we use rho 1 to denote lambda 0 divided by mu 1. Then rho 2, if we move this lambda 0 equals to mu 1 P1, and then we will be able to get, you see, mu 1 P1, mu 1 P1 canceled. So this actually equals to P2 equals to lambda 1 divided by mu 2, and then lambda 0 over, this is lambda 1 over mu 2 P1, actually, P2. So Let's use rho 0 equals to 1, rho 1 to denote this ratio. And then rho 2 denotes lambda 1, mu 2, lambda 0, mu 1. And we continue to do that. And in general, rho I equals to lambda 0, lambda 1 to lambda I minus 1 divided by mu 1, mu 2 to mu I. So this is a ratio. Okay, burst test ratio. Okay. And now, because the P1 plus P2, P0, P1, P2 to Pk, this is equals to 1. And Pi equals to rho I P0, because if we organize this equation, we can see this rho I, put it in, and Pi equals to rho I P0. Okay. So we add all of them together. So P0 is actually equals to 1 over all the summation from rho 0 to rho k. So this is the general results for P0. And the Pi equals to rho I P0. So we just put a rho I on the top. So we got a rho I equals to over the summation of all the rho I. So this is also true for 0 to k. So this is the general results. Okay. Now we got the limiting behavior. If lambda I equals to mu, mu I equals to lambda I equals to lambda, mu I equals to mu. Okay. Let's define the ratio is actually lambda over mu. Then because this is lambda over mu, this will be rho squared. So rho I will equals to rho power I. Okay. And rho 0 equals to rho power 0 equals to 1, still the same, rho 0 equals to 1. Now let's assume this lambda over mu, lambda does not equals to mu, okay? Rho doesn't equal to 1. Then we sum all the rho I together, and it will become rho power I. It will then, based on the series, we will be able to get 1 minus rho k plus 1 divided by 1 minus rho. And then this is, if we flip it, because P0 equals to the 1 over this summation. So we got a 1 minus rho k plus 1. So this is a limiting behavior for if rho, we have constant arrival and a constant departure rates. Then Pi equals to P0 rho I. Okay, so this is rho power 1, rho power 2, and then rho power I. So this is the general form of the Pi limiting this probability. Now if lambda and mu equals to mu, then rho equals to 1, then Pi is actually, if you add them together, this is actually k plus 1, because this is lambda over mu is 1, right? So it's 0 to plus all the way to k. It will become k plus 1. So Pi equals to 1 over summation this, so it will become 1 over k plus 1. And because every time you multiply by rho is 1, so every Pi is 1 over k plus 1. Okay, if rho equals to 1. But in our case, rho and the mu, they don't equal to each other, and the lambda and the mu, they are not, that does not equal to each other, does not equal to each other. So now we got the limiting probability for MM1KQ. So this is what we have for the car model 1, because we have arrival process and departure process in the parking lot in steady state. So what's the expected number of cars in the lot in steady state? So this will become L equals to J equals to 0 to K1, because we, in the policy, we set it to be K1. So it will be J PJ. This is a limiting probability. This is the expectation. So the inventory cost, if we stock like in average L cars, each car costs 8,000. So the inventory cost will be 8,000 L times L. And in order to maintain this inventory in the parking lot, we need to pay the insurance premium and also maintenance fee. This is about 1% of the average value of the inventory. So the cost to maintain this number of cars is 8,000 L times 1% is about $80 and times L car. And we also have car sales. Car sales is a net profit, and we want to calculate the net profit. This is 16 cars per week. So we're going to have sales if we have cars in the parking lot. That means state 1 to K1, we can sell the cars. No cars will be sold if there's 0 cars in the lot. And each car, the profit is 10%, okay? Because we sell the car 10% markup price, okay? At 10% profit. So this will be $800. And then 800 times 16 times maybe P1 plus P2 to PK. But this actually equals to 1 minus P0. So car sales brings the net profit, brings a profit like 1 to 800 and then 1 minus P0 and then minus the maintenance cost. Maintenance, keep this inventory, we need to pay in premium and the maintenance fee. So this is a net profit. Here, P0. P0 is a function of K1. As we can see, P0 is a function of rho and K1, but we know lambda and mu because lambda, we have supply rate and demand rate. And this will be K1. So P0 will be a function of K1 and L is function of K1 because this is PJs, they are also function of K1. Now, this net profit is function of K1, and we can calculate this for every car model. And then we got GI, KI. We add all of them together. This is a weekly profit for if we have this policy, K1, K2, K3, K4, K5. And the constraint is add all of them together less than 40. So the optimal stocking policy, we want to know the optimal stocking policy. We know every net profit, every car model has a net profit function. It's actually the function of the stocking level, okay? It's a function of the stocking level. And we know the supply demand rate. And we know the L is also a function of K1. Now, what we want to do is maximize the profit and adjust the K1, KI, K1 to K5. But we want to subject to this constraint less than or equals to 40, add all of them together. And the KI should be integers. And now we have 5 net profit functions. They are all functions of KI. We need to optimize over maximize this net profit, the summation of net profit, and find the K optimal stocking level. So here's this figure shows the net profit function for car model 1, so G1, K1. So this is K1, and this is net profit function. You can see that this is a concave function, and it reaches the maximum at 10. Now we are going to use because this is concave, and we're going to solve this optimization problem with the greedy algorithm. So the allocation algorithm is first step. We're going to initialize K. So this for 5 models, they are all 0 stocking level. Now we're going to compute the gradient. So this is gradient for every net profit function for each car model, I equals to 1 to 5. We calculate the gradient. And we're going to find the index, which car model actually gives the maximal gradient, the highest incremental profit, which car model. Then if that car model gives the highest incremental profit, and at the same time, now if we sum all the KI, they are still less than 40, and this gradient is greater than 0, then we find this index, the car model, we add 1. Okay, then we continue to iterate this process. Then we calculate the gradient again. And then we find the car model gives us the highest incremental profit. Then we add the stocking by 1. Okay. So the step 4 is all spots. If all spots are allocated, all the gradient is less than 0, we stop. Then K, this K will, the final K will be the optimal allocation vector. Okay. So now, based on the optimization algorithm, we got the optimal policy, stocking policy. And then we compare with the 2 policies that we had before. That is average policy of prioritize the most expensive car, and the smaller one of the supply and demand. So for this one, the expected weekly profit is 76085. And policy 2 seems to be more profitable, but this one actually didn't bring us more profit. It actually worse than the average stocking policy. For the optimal policy, optimal stocking policy, we actually got the profit 76318. So this is the best one. However, when we derive this optimal policy, we have made several assumptions. That means we have fixed price, right? Purchase and selling, and we always have 10% markup. And what about the market price? Actually, dynamic change. And also here we're using a static policy, and but the policy can change over time. The current mix of cars in the parking lot actually impacts how many you are going to stock. And also demand and supply depends on the price. So if you are going to consider all this, relax your assumption, this dealership market dynamics will become more and complex. Okay, there are more to think about how to apply the CTMC and also the MM1K Q models to study the optimal stocking policy for the dealership market. Okay, especially to investigate the optimal stocking policy for a small car dealership. So here's my contact information. So this concludes today's lecture on car dealership market and CTMC modeling.